Hi, thank you for the introduction. Well, first of all, let me say that we have a very long title, and as you see, we are trying to mix some computer theory plus more practical stuff, okay? I'm gonna try to make the introduction a bit fast, so in case that you have some questions or whatsoever, just raise your hand and let me stop, okay? Well, I'm the one at the right, still alive. I'm working as assistant professor at the Centro Universitario de la Defensa, which is the university center in the General Military Academy in Spain. That means that I'm teaching the military people. But apart from that, my research interests are more focused on the malware analysis, RFID or NFC security, plus the security-driven engineering. Well, this is Daniel Uroz, the guy who implemented the tool that I'm gonna introduce you here. He's a bachelor in informatics from 2 years ago, more or less. And now he's working with me at the University of Zaragoza. Well, this is the agenda for today. I'm gonna introduce the topic, then I'm gonna introduce you the tool that we have developed in the regarding this study. Then I will tell you the evaluation that we have done. And I will show a little demo. I will try to show a little demo with Windows 7. And then I will close with the conclusions. Well, going to the introduction, I think that we already know that software systems are very large, very complex. In fact, if we read some papers on this about software vulnerability metrics, we can read that there is like between 6 to 16 software bugs per every 1,000 lines of code, approximately, okay? So this means that we have a lot of vulnerabilities, okay? Because you know that when people are developing new software, they are more worried about the time to market. I mean, they want to complete the product as soon as possible in order to get more customers or get more revenue whatsoever, okay, instead of focusing on the security of the product or other kind of stuff. Well, the thing is that some of these vulnerabilities can also raise software memory errors. When we have these software memory errors, we can talk about control flow hijacking attacks. These kind of attacks are a special attack in which the legitimate control flow of the program, I mean, if the program has to go from A to B and from B to C, it means that when I have a control flow hijacking attack, I can do the program to go from E to C directly, with avoiding going to B, okay? So when we have these kind of attacks, it means that we can insert arbitrary code, any kind of code, and we can execute this code, okay? There are different defense approaches when to avoid this kind of stuff. We can talk about control flow integrity approaches, type-safe languages, stack cookies, inline software words, okay? Or we can have also another kind of defense mechanism, which is to try to isolate malicious code prior execution. For instance, tainting analysis, runtime elimination, or write-store execute, which also is known as data execution prevention. I would like to recommend you here this paper from some years ago, in which present this kind of stuff about software memory errors in a very detailed way. Well, let me talk a bit more about write-store execute. Write-store execute is a defense mechanism that it's widely used, actually. In fact, almost every current operating system incorporates this kind of defense mechanism natively. The main idea of write-store execute means that the memory pages of a process are either readable or executable, but they are not both, okay? So we can have memory pages in which I can write and I can read, but I cannot execute. Okay, or otherwise I can have a memory page in which I can read and execute, but I cannot write. Okay. Anyway, if we have this kind of, let me know that if we have this kind of defense mechanism, the adversary, the attacker, can always still inject code. Okay, but the thing is that this defense will prevent the execution. This is important to be noted. Talking a bit more about write-store execute, there is hardware support. I don't know if you know these terms. In AMD is NX bit, and in Intel they call it XD bit. Okay, this is the hardware support for the write or execute in memory pages. And there is also software support. We have in Linux from the PAX project, and, which comes, by the way, from OpenBCD. And in Windows, they incorporate this defense from the XP, SP2 onwards. In Windows, write or execute are called data execution prevention. Maybe you know this term more. Okay, I don't know why by Windows, you know, guys, that they are always renaming every fucking thing. Okay. Well, the thing is, okay, I have this write or execute mechanism defense. How can I try to defeat this protection? Okay. So if you want to exploit memory error, for instance, stack buffer overflow, it means that you want to write some stuff in the stack and then you want to jump into the stack. Okay. However, since the program is defended with write or execute protection, we cannot execute the stack, because in the stack we can write or we can read, but we could not execute because of this defense. That means that as attacker, you are fucked. But wait a minute, it means that, let me remember you that I told you that you can always inject code or inject things, but you will not be able to execute. This is the thing of the write or execute defense. So, since we can write in the stack, everything that we want, and the stack, let me remember you that also stores the return addresses of the control flow. Okay, when I have some call in the program, the return address will be stored in the stack. That means that when the return instruction is executed, the return address is taken from is popped from the stack. Okay, so since we can write in the stack, why can not we write directly into the stack memory addresses that point to already existing code? Can we do it? Yes. This is the main concept of the ROP attacks, or return-oriented programming. This means that I'm going to insert into the stack just addresses to memory addresses. I'm going to insert into the stack memory addresses of code that already exist in the memory process. Okay, in the process, in the memory of the process. So, since these memory pages already have the execution privileges, it means that these pieces of code that I'm setting into the stack will be executable. Okay, and this means that since these pages are executable, they will not be captured by the write or execute defense mechanism. Okay. So, roughly speaking, return-oriented programming allows an adversary to induce an arbitrary execution behavior while injecting no code. Okay, the attacker will use addresses of existing code in the process memory. So, what is the thing here is that we are talking about, for instance, if we focus on Intel x86. Let me remember you that the instruction set architecture has a variable size. This means that if we have an instruction like this one, okay, this is a legitimate instruction that we can have in our code. For instance, I don't know what is doing this code, but I mean the general code. But in this instruction, we are setting this value into this register. Okay. However, if we start to read the instruction instead of this opcode in this other one, this instruction will become in this other one, okay? But note that here we have a move instruction from a register to an address in memory, but the good thing is that we have here a read instruction, a return instruction, okay? So this thing of here is what is called a ROP gadget, okay? This is a small piece of code which ends in a read instruction, okay? So what can an attacker do is just to mix all these ROP gadgets in order to conform a ROP chain, okay, which is a set of these ROP gadgets, in order to do the computation that he wants. For instance, I have here an example. Imagine that I have in these addresses these instructions, okay? What I'm doing here is just I'm popping out a value from the stack, and I'm setting that value, this one in this case, in the ECX register, and then I'm returning. So the execution will be returned here. We'll get this instruction to see what it has to be executed. In this case, it will pop up another value into the EDX register, and so far and so on. Okay? So this is what the attacker will do when we are doing a return-oriented programming attack. Okay? The attacker will insert this stuff into the stack. Let me remark that the attacker is not executing, the execution is not on the stack, but on the original pieces of code of the program. Okay? So, as I was saying, the adversary will be able to control the order of execution, okay? Because once he sets the ROP gadgets, he can determine how will be the order of execution. So, how can we, knowing this, how can we defeat the write or execute protection? Well, we can build our ROP chain to deactivate the protection. We will need, as an attacker, to set the CPU registers in the first term to specific values, and once we have this, then we need to call some system call in order to disable the protection. Okay? For instance, in Linux, we can do it by executing the memprot syscall, or in Windows, since they are very nice, they provide us this API, set the process policy, which just receives a boolean in order to deactivate or activate the protection. Okay, and so far and so on. Well, let me introduce you here a term, executional adversary power, which means that the power of the attacker, or the adversary, will be equal to what he can execute. And this will be determined about which are the already existing code in the process memory. Okay? So, here we have a Turing. Let me recall you, if you are not very very related to computer science, that the Turing hypothesis tells us that any real-world computation can be translated into an equivalent computation involving a Turing machine. Okay, this was said by Charles and Turing in the, I don't remember exactly the date, but a few years ago. Okay, so considering this hypothesis, we think that if we can find any kind of ROP gadget that implements all the operations of a Turing machine, that means that the attacker will be able to do whatever he wants. Okay? This is what I have told you here. We can build a type of Turing machine. It's more specifically, it's a random access machine that performs equivalent computation as the ones performed by a ROP machine. So what are the operations in a random access machine? Are just these ones: load a constant into a register, move a register to another register, load a value from memory, store a value into memory, the add and the subtract, the logic operations, okay? By the way, by the Morgan laws, we only need one of this set plus another one of this set, okay? And also we need to perform conditional branches. So with all these operations, we are able to simulate any kind of real algorithm, okay? So our work hypothesis in this work was, well, if we are able to find at least a single ROP gadget for each one of those operations, then it means that we can solve any computational problem, okay? Well, the random access machine operations defined as ROP gadgets can be, for instance, this one of here. So here we have like 4 different ROP gadgets, but let me tell you that every one of these are implementing the same operations, okay? Each one of these are implementing a move operation, okay? In a semantic way, they are implementing a move operation, okay? I'm not gonna go further on the assembly instructions. If you wanna discuss later, we can do it, okay? So, considering this, we would like to evaluate the executional adversary power, okay? As main contributions in this work, we have developed a tool, which is EasyROP, which takes as input a binary plus a ROP chain specified as the as the operations that we have seen before in a text file, and as output, the tool will give you directly the ROP gadgets to implement that ROP chain. Once we have developed this tool, we have applied this tool to evaluate the executional adversary power in Windows, since Windows still are the predominant platform for attacks, for attackers. And we have considered Windows in different flavors, from 32 to 64 bits. And I will also show you how to apply the tool in order to generate a ROP chain for exploiting a real vulnerability. Okay. Well, regarding the tool, let me tell you that we have developed it with Python. Our main idea was to make the tool multi-platform. And the main idea behind the tool was also to try to automate the construction of ROP chains, just allowing the user to specify the ROP chain as Turing operations. Okay. And one of our main was also to try to make the tool in order to allow extension. Okay. Currently, our tool just supports Windows binaries, but it's very easy to extend it to another platforms. We have also developed the tool that not only considering the Turing operations or the random access machine operations, but also user-defined operations. Okay, we allow the user to define which operation he needs, and once he is defined, he can use the tool in order to find the ROP gadgets. So we have used Python 3 instead of Python 2, and we also have used Capstone disassembly framework. In fact, our tool is part of the Capstone showcases on the website of Capstone. And for the user-defined operations and for defining the Turing machine operations, we have used XML. Maybe it's a bit old, but we are still working on it. Regarding the automation of the creation of the ROP chains, consider that we have, for instance, you want, for instance, to create a ROP chain with this operation. So I mean, to load a constant in the ECX register, to load a constant in the EDX register, to move the value that I have in ECX to another register, rec3. That means this is a mask. It could be any kind of register. I don't care about the register. And then to move from that register to another register, okay? Again, a mask. So if we execute the ECROP with this chain, we can get, for instance, this kind of stuff, okay? Here we have the load constant in ECX register. Here we have the load constant in EDS register. And here we have the move to a rec3 register. In this case, the tool considers rec3 like EAX. And here we have again from the rec3 to another rec4, okay? In this case, EBX, okay? Everything is just done by the tool. So besides doing this stuff, as I was telling you, the tool also allows to define allow the user to define his own operations. Okay, we have used XML, so we have an DTD file in which we define how has to be every operation. Okay, so in this case, here is the defining, for instance, how we can make a move operation. Okay, so we can do a move operation by clearing a register, and once we have the register, then we can add to that register another register. Okay, that means it's equivalent to a move operation. The tool was released under GPL version 3 license. It's on the GitHub. So here you have the URL. I have already given the slides to Dylan, so I think that it will be online soon. Well, regarding the evaluation, our idea was to try to search for at least one ROP gadget for every random access machine operations. Okay, So, considering Windows, we have used a subset of the known Windows object, which is in this case is a internal operating system object in which contains the most used system DLLs. From these ones, we have taken all of these ones, which are under our criteria the most common ones when we are developing when we have an application developed with Windows. And we have also considered this other DLL, which is always loaded with Windows because it's part of the Windows image loader, okay? It's part of the thing in Windows that allows to execute, that puts on memory every single binary. As test environment, we use personal computer plus the VirtualBox. So we recreate 8 virtual machines from Windows XP to Windows 7, 8.1, and Windows 10 Education in both 32 and 64 bits. I'm sorry for the Vista lover guys that we haven't considered it. Okay. Well, regarding the evaluation, this is what we got. If we consider this DLL, which deals with everything related to shell, for using shell from an application, plus NTDLL or kernel 32, we have enough gadgets to conform every one of the random access machine operations that I have told you before. Okay, that means that if we have a process which has this DLL loaded into the memory, and this process has, or this program has some kind of vulnerability that we can exploit in order to execute arbitrary code, that means that we could execute whatever we want, okay? If we do not consider the conditional branches, just with the NTDLL, we are able to do whatever we want, okay? Let me tell you that when we did this research, we defined the conditional branches in a specific way, which is not very complete. Let me say in that way, okay? So we could even extend the definition of how the conditional branches can be done with ROP gadgets. In that case, if we are able to extend this definition, we could have better results, okay? We could find, for instance, that just with a single DLL, we can do whatever we want. So regarding the case study, I have used this vulnerability CVA 2010-3333. It's a Microsoft Office vulnerability that affected to almost all the suite of Microsoft Office from the XP to the 2010. It was disclosed in September 2010 and patched in a bit later, okay, in November, in the same year. The thing is that this vulnerability was used in 2012 to attack the NATO Special Operations headquarters, okay, this is the thing. The attack was delivered by spear phishing, attaching into the email just a crafted file, namely an RTF file, that was exploiting this vulnerability. An RTF file is just like this one of here. Okay, so we have a lot of text stuff enclosed by brackets. Okay, and in particular, the vulnerability was exploited using these attributes of the RTF specification. So let me tell you that, well, we have like 2 years, right? From the patch to the attack. So please update. It's free, almost. Well, let me tell you a bit more about this vulnerability. This vulnerability is a stack-based buffer overflow in a function, okay, which was in charge of parsing the RTF file. For instance, consider that we have this DLL, which is the one that is exploitable, this version from the Microsoft Office 2003. In one part of the RTF parser, we have this code in which we have a call to this other function, okay? Here, what they are doing is just a memcopy, it's like an inline memcopy, okay? And the thing is that in this inline memcopy, we have here, yeah, in this instruction, he's doing the buffer overflow, okay? So if the attacker is, can build an RTF file, a crafted file, with some specific values in these attributes, he is able to exploit this vulnerability, okay? Which is just a buffer overflow. So, well, how we can build a ROP chain in Windows? Consider that we have a Windows 7 in which we have activated the, with EMET, we have activated the data execution prevention defense policy. In that case, we need to call to this function, setProcessDevPolicy, that, as you see, it will receive just a flag informing that a Boolean flag, true or false, in order if you want to enable or disable the dev policy. Okay. So consider that we know the function address, okay, because there are some other memory leak on the program, or we have some other kind of stuff running on the victim, and then we can know this kind of stuff. So what we are going to do is just to build a shellcode in order to prepare the registers and call this function in order to disable the protection, okay? So I'm going to do it just using the pushat instruction, which is a instruction from the Intel set architecture that allow us to insert every one of the registers into the stack, okay, in this order. My ROP chain will need to set the registers in this way, okay? And after execution, the execution of this instruction, I will have on the stack this thing, okay? So once I do everything, let me note, okay? So I will need will be an op, okay? Then I will need to load a constant in EDI, load a constant in the SC register, load a constant in EBX register, load a constant in EVF register, and then the pushat, okay? Let me tell you, for instance, all of these are, these 4 instructions are random access machine operations. However, these others are not random access machine, but user-defined operations, okay? So I have this definition. I go through the tool directly using the own file, which is vulnerable because it is not protected. It's not protected neither with the ESLR, so we can also use that because all the memory addresses are fixed. And then if we execute the tool, we will see that it takes around 1 minute and a bit, okay? And it will give us this, okay? Let me do it. So consider that we have, for instance, this ROP chain, which is the one that I was telling you. You see, okay? Yeah, okay. So I'm gonna execute the tool and I'm gonna say, well, get the MSODLL, build a ROP attack, which is specified on that file, okay, which is the one that I have just showed you, and try to avoid the jump, well, the instructions that ends in a jump and the instructions that ends in a far return. And def2 means that I want just gadgets with 2 bytes, okay? I don't want larger ROP gadgets. So I can execute it, fingers crossed. In the meantime, let me also show you okay, I have here a Windows machine with some personal stuff. Here we have an RTF file. Okay. So you see it's an RTF file, okay? And if we open the file, I have here, just a sec. Okay. So you see, this is the content of the file. It's just an RTF file with a lot of stuff, okay? And here we have our shellcode, okay? Here we have the padding, and after the padding, we will have the instructions that we will get from the addresses that we will get from the easy ROP tool. Okay, so this is an RTF file. Let me tell you that I have also emmet installed in this machine. As you see, data execution prevention is always on. It means that there is install, is activated. Okay, and if we just execute the file, let me minimize all these windows. If I just execute the file, have you seen something strange? Well, this is the typical stuff, right? I have just executed I have just popped a calc. Okay. If we check with the hacker process, you will see that the parent of the calc are the Word. So that means that it was launched by the Word, Microsoft Word program. Okay. And of course, it's completely functional. Okay. Well. This is the execution of the easy ROP, has already finished. As you see, it takes like around 1 minute in my laptop. Okay, and it will give you for every one of the ROP gadgets that you have specified the possibilities that you have. Okay, in this case, in this DLL, we have only these possibilities. If you try with some other, you will find that you can also exploit with some other DLL. Well, blah, 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 yeah. Well, we have developed this tool which allows us to automate the construction of the ROP chain, specify as random access machine operations. It also allows the user to specify its own operations. And we have evaluated the executional adversary power in different Windows OS. Okay. We have found that the power is more powerful in 32 bits than in 64 bits. And that if we consider only this DLL plus some of the other set, we can have everything, we can perform any kind of machine, random access machine operations. Okay, and this is all that I have to tell you. So thank you for your attendance.
Thank you, Ricardo. We've got time for just one question. Otherwise, no, you were actually the first one and the only one, I guess. There you go.
We can share. We make a half question. Yeah. So I saw there was a table. I saw there was a table where with X and I mean where you have 32-bit and 64-bit for operating systems, but you didn't describe it, or maybe I missed it. Somewhere in the middle, like.
Papa,
yeah,
this one? Yeah, oh yeah, sorry, yeah, I forgot. Here is where we find enough gadgets for performing all of the operations, and the cross means that we have some failures. In fact, in all these crosses, the only failure that we have is the conditional branches. We are not able to find the conditional branches. But as I was telling, that I forgot to tell, thank you, David, is that the main problem is that the conditional branches was specified in a very specific way. So we need to try to look for a more general way to describe how to perform conditional branches.
Second half, same slide. Okay.
Thank you.
Second half of the question, same slide. Did you, for searching the ROP gadgets, limit the size of the gadgets as well? Or
yes.
Because if you limit it to 2 bytes or something, then of course...
No. There are some kind of... no, it was not limited.
Not limited?
Not
okay,
limited.
so with side effects as well, like...
This is the other thing that I think I forgot to put on the slides. Now that you told me, yes, I forgot. As future work, we need to work on the side effects of the gadgets. Okay, right. This is one of the things that we need to deal with. Thank you.
Right, perfect. Thank you.
Okay, there you can see that our audience is still very sharp, even after maybe yesterday evening. Well, thanks very much.